Sounds good.
So welcome everybody once more to the official IAU G2 online conference series. As usual, this is about massive stars, and today is my real pleasure to introduce our next speaker, Maria Drout. At present, Maria is Associate Professor at the Department of Astronomy and Astrophysics of the University of Toronto. She completed her PhD thesis in astrophysics in 2016 at Harvard University. The title of her thesis was Peculiar Transients as Proofs of Stellar Evolution and Mass Loss. And afterwards, and before moving to the University of Toronto in 2018, she was also a NASA Hubble postdoctoral fellow at Carnegie Observatories. There's already a lot of movement here and there. As stated in her CV, which I found that is quite amazing in many aspects. So congrats for that, Maria. The goal of her research program is, broadly speaking, to understand the life and death of massive stars and their relation to the origin of unusual astronomical transients. And in this context, her approach is to combine multi-wavelength observation of transient phenomena with studies of resolved stellar population. No? And probably she will be explaining, the way she's doing this is combining different areas like multi-messenger gravitational wave astrophysics, new regions of transient astronomy, and also stellar astrophysics via population statistics. She has been interested in studying objects like supernova, yellow and red supergiants, and recently she has been also interested in the detection and characterization of intermediate mass helium stars that have been stripping binaries, a research line that she will be explaining us today. So on behalf of the IAU G2 Commission, I would like to thank you, Maria, for accepting our invitation to deliver this online seminar today. And whenever you want, the floor is yours. Thank you very much.
Wonderful. Thank you, Sergio. And yeah, thank you for the invitation to give this talk. I was also very happy when we figured out it was in that 2-week window when Europe and North America have a smaller time difference. So it's not too early for me on this end as well. But yeah, I guess diving right in, we were told we could actually start with just a brief overview of the overall research program. So I did just want to have one slide. Sergio touched on this a little bit already, but emphasizing the fact that emphasizing the fact that at the University of Toronto, our massive star group, we really are looking at this from multiple angles. About half the group studies transients, whether it's core collapse supernova or other peculiar transients, and the other half is studying stellar populations. We're really trying to piece together things, both understanding how different types of supernova explode, what their progenitors are, what the evolution of massive stars is towards their eventual supernova explosions or other endpoints, and then also multi-messenger gravitational wave astrophysics. So doing electromagnetic follow-up to gravitational wave events found by LIGO and Virgo, and really trying to piece together all of those things. And as I said, about half the people are working on transients, half working on massive stars, but really trying to mesh those two angles together. However, what I was going to talk to you about today is slightly more focused as opposed to that very broad thing. I want to talk a little bit about stripped helium stars, which is some exciting work that we've been doing over the last couple of years. So this is the broad overview for what I'm hoping to cover. I'm told to keep it to about 40 minutes, so there was plenty of time for questions. We'll see if I get through everything. But my plan was to give you a little background. What am I talking about when I say stripped helium stars and why they're important? Briefly give you an overview of how a couple of years ago we discovered a population of these stars in the Magellanic Clouds, and then hopefully spend about half the time on what are we doing now with this population, talking a bit about population statistics, mass loss rates, and binary properties. And if I have time at the end, some other fun things we can do with the types of data sets that we've been finding for this work. So diving in, I also just want to acknowledge that a lot of the results I'm showing here depended on quite a few people. This is a big highlight of them. A lot of this work sort of evolved out of a collaboration between myself and a bunch of people at the University of Toronto and Ilva Goldberg, who is currently at ISTA, her group there, as well as some people elsewhere. I do want to call out in particular Bethany Ludwig, who did her PhD thesis on a lot of this work and just defended back in December and has now moved to Leuven. So for those of you in Europe, please go and say hi to her there as well. But yes, there are many other collaborators who are involved in this work as well, but these are just some of the main people whose work I'm going to be showing on some of the slides in a little bit. Okay, so some background. When I say stripped helium stars, what am I talking about? I am referring to a star that has lost most of its hydrogen envelope via binary interaction, whether that is a star that underwent stable mass loss through Roche lobe overflow or something more extreme like common envelope evolution. But this process of having its hydrogen envelope stripped off reveals a hot helium core. That is what I'm going to be talking about. This is a slightly more theoretical view of what this might look like on an HR diagram. This is an example of a star maybe that starts here. If you can see my mouse in the main sequence, evolves in the main sequence. As it starts to cross the Hertzsprung gap, its radius expands dramatically. It will start to overfill its Roche lobe. At that point, it will undergo an interaction, and then it will eventually contract and live out most of its helium core burning life as this hot and compact and hydrogen poor star. There are other types of strip stars that can exist at cooler temperatures, whether they're inflated or partially stripped. But for most of this talk, I'm going to be focusing on the types of systems that we expect to live over here. So at very hot temperatures, compact radii, and for cases where these stars evolved from stars with initial masses between, say, 8 and 25 solar masses, they're expected to have roughly intermediate luminosities between subdwarfs on the low mass, low luminosity end, and Wolf-Rayet stars on the high mass and high luminosity end. Those are the types of stars I'm going to be talking about. And as by way of background of why we think these should be common and also important, these types of systems, we now know quite well that multiple star systems are essentially ubiquitous, especially on the high mass end. There have been many compilations of this. This was a recent compilation in Stella Offner's review article showing the multiplicity fraction of stars as a function of primary masses. And you see that it approaches essentially 100% for the massive stars, the O and B types. In addition, when you actually put those types of initial conditions into models for binary evolution, the predictions are that strip stars of the type that I just described, where they undergo this interaction that removes much of their hydrogen envelope, should be relatively common. Something like 30% of OB stars are expected to go through this process. In addition, these types of stars that, again, have undergone this binary interaction, which removes most of their envelope, are expected to be, or at least right now, they are the favored progenitors for most of the hydrogen-poor core collapse supernova that we observe. This is the angle I actually came at this from initially. I did a lot of work on understanding hydrogen-poor core collapse supernova. And what I'm showing here is just one example. These are the derived ejecta masses for a set of hydrogen-poor core collapse supernovae. Ignore the different subtypes for now, but the main point is most of the ejecta masses we infer are between about 1 and 4 solar masses, which are more what you expect from binary or from stellar evolution models if they are originating from slightly lower mass stars that have had their envelopes removed via binary interaction versus more massive stars that have had their envelopes removed primarily via winds. In addition, it is thought that we need multiple phases of mass stripping in order to produce binary neutron star mergers of the type that LIGO and Virgo are now detecting. This is one schematic of a possible evolutionary pathway to go from massive main sequence binary all the way through multiple phases of interaction and to eventually get to a neutron star merger that will merge within a Hubble time. And the main thing I want you to focus on is there are a couple of phases here where the star undergoes envelope stripping. So here is one example at the beginning where the primary star is stripped and you have a phase where you have a helium star with a main sequence companion. But then the system will continue to evolve and is thought it might have to undergo common envelope evolution, where again, then the secondary becomes strips. And in this case, you actually have a helium star with a compact object. So this is one pathway to get there. And you can see there are multiple phases where we are predicting stripped helium stars with various companions around them. And finally, I know all of you who are at this are probably excited about massive stars for many reasons. But in addition to the stellar evolution itself, if you want to understand the light from stellar populations, you really do want to understand these stripped helium stars as well. Because they spend a decent chunk of their lifetime as hot sources, they can actually produce a non-negligible contribution to the hard ionizing radiation from stellar populations. This is one example that Ilva Goldberg produced of a population with continuous star formation, but after 500 mega years, you find that stripped helium stars can actually be a dominant source of hard ionizing radiation over the more massive stars, which would have evolved more at this point. So despite that, so I mostly hope I just convinced you that these things are important. We do expect that they should be there. However, despite that, until recently, We didn't actually have an observed population of the stars, specifically ones that we thought originated from stars that initially were in this mass range of maybe 8 to 25 solar masses, which were predicted to yield helium stars between about 2 to 8 solar masses. And these are things which we would expect could eventually explode and maybe form neutron stars. We didn't really have a population of these systems. So this was a question of how do we actually try to find them? So one way to do this, and this was the direction we as a collaboration took, was to look for systems that had extra UV light. So the reason this might work, what I'm showing you here is an example of just the spectral energy distribution expected for a 4 solar mass strip star, shown in blue, and a B-type star with about 5 solar masses is shown in red on top. And the main thing I want you to look at when you're looking at the wavelength range, we've labeled here roughly where the optical is and where the ultraviolet is that, these two stars might actually have similar energy output in the optical, not so different slopes actually even through this phase. You might expect similar optical colors from these two types of stars. But as soon as you get out into the ultraviolet wavelength range, you see that the strip stars can, because they are quite hot, produce and yield even more light than what this B star might have. So this leads to a method where you expect some of these stars, if they are systems that have a B-type star with a hot companion, you might be able to look for systems with excess UV light. So here's just an example of how this might work, and then I'll show you what we actually found. So this is an example, just a color magnitude diagram where this is UV light on the vertical axis and a UV minus visual color on the horizontal. I'm going to be showing you a few of these throughout this talk. But this is an example here of where the zero-age main sequence is expected to be, and it's labeling stars of particular masses here. This is now what you'd expect for stripped helium stars just from the light from those stars themselves. You see they're located at much bluer colors is this side, and that is because they have much hotter temperatures despite having similar luminosities to main sequence stars of this type. So you can see this is where they would be expected to lie if you were only looking at a hot helium star. So then you can just do the exercise of combining light from the two of them together. Here's an example of if you had a 4 solar mass strip star plus a roughly 5 solar mass main sequence star, you would expect the system to lie here. So this is a system that is bluewards of the zero-age main sequence. So again, similar overall brightnesses to B-type stars, but have extra UV light, so bluer colors than you would expect just from main sequence stars themselves. And if you sort of put this grid together, comparing different masses of strip stars, different masses of main sequence stars, you end up with this region here spanning the zero-age main sequence to the helium stars where you would expect some stripped helium binaries to lie. However, in order to do this in practice, this means we need good UV data for a large stellar population, which it turns out the community is doing a very good job at getting better at this, but was actually somewhat lacking. So what we decided to do was we decided to look at these maps that had been created by the SWIFT telescope. SWIFT is a satellite that initially was launched to look for gamma ray bursts, but they also have an X-ray and a UV optical telescope on board. And about 10 years ago now, they actually did a mapping of the large and small Magellanic Clouds. It was about 150 pointings for the LMC, which is what I'm showing here, and about 50 to cover a large chunk of the SMC. But at the time that we started, there wasn't actually a point source catalog available for this data yet. So this was work that was led by Bethany Ludwig at the University of Toronto, is going through and actually doing photometry on all of this data. It turned out it was challenging. The point spread function of SWIFT is about 2.5 arc seconds, and the Magellanic Clouds are crowded. So you really need to do point spread function photometry. And Bethany helped develop this. She developed a pipeline where she took a forward modeling code called the tractor, and you actually take the known location of sources and forward model what their exact positions and magnitudes are to reproduce the images. So what I'm showing you here is this is a real image or data on the left, and this is one of the models Bethany produced for that image on the right to sort of extract the magnitudes for all of these sources. When you do this, you get observed color magnitude diagrams that look like this, where all the points are unknown data. You can see here is where, again, the ZAMS is. And you can see there are a wealth of sources that are actually bluewards in that region where we would expect stripped helium stars to be. So what we did at that point initially, and what you've probably seen a number of us give talks on already, is we obtained spectra for a large number of these. And what we found is that they fell into 3 main spectral classes. So one is that I'm showing you here on the top. They were stars. I'm not going to spend too much time on this, but just to give you a sense of what we're seeing here. These are stars that, if you're showing in blue, they show helium-2 in absorption, indicative of a hot star, but they do not show very prominent Balmer lines over in the blue, which is what you'd expect for a B star. So this top type is actually consistent with what you'd expect for a spectrum that is dominated almost entirely by a hot helium star. We then had a set of objects, which you're seeing in the purple here, where you do, again, if you look at these blue, you do see the helium-2 absorption, which is indicative of a hot star, but you can see more prominent Balmer lines are showing up in this region, which also indicates the presence of a B star. So this would be expected if you actually seeing light from two different stellar components. So both a slightly cooler B star with strong hydrogen lines and a hotter star as well. And then in the bottom, you see an example with very prominent Balmer lines over in the blue, and you don't actually see evidence of helium-2 in absorption, despite this object seeming like it has excess UV light in its spectral energy distribution. And it turns out this set of classes of objects is exactly what you would predict if you were seeing systems where you have helium, hot helium stars, and also B-type main sequence stars where they are just contributing different ratios of the total optical flux to the system. So again, strip star dominated on the top, down to main sequence star dominated on the bottom. This is what you'd expect. In addition, though, you can go through and actually do spectral fitting for these objects. And this is what we did. Ilva Goldberg put a ton of effort into this, creating a new model grid for helium stars with a range of surface hydrogen mass fractions, temperatures, and surface gravities, and actually do spectral fitting for this sample. And what you find is that they do have hot temperatures in the range of about 50 to 100 kilokelvin. They're compact, about a solar radius, and they are hydrogen poor, with hydrogen surface mass fractions ranging from almost 0 up to about 30%, all of which are consistent with being stripped or hydrogen poor stars. And what's in particular notable is this is consistent with what the predictions were for stars that were stripped via binary interaction. In particular, if you look at the HR diagrams, which I'm showing you here on the left, you look at their luminosities and their temperatures, and their luminosities, again, are in this intermediate range. And they are consistent with what you'd expect for stars that are currently in their core helium burning phase from stars that were, they are strip stars in the range of about, 1 up to 7 solar masses, which is consistent with stars that initially had masses in the range of about 8 to 20. So again, these seem to be stars that are consistent with this prediction for the stars that should be intermediate between the subdwarfs and the Wolf-Rayet stars, so sort of filling this gap. So that's great. Wonderful. It would have been a big problem for, I think, all of us in this Zoom call if there had been no strip stars. Because again, as I pointed out, there are many different reasons, many lines of evidence why we thought they should exist. And there had been a handful of cases, but it looks like there is now this larger population, which we're just at the tip of the iceberg for now. But where I want to spend actually much of my time in this talk is telling you what we've been doing now with these. Because again, obviously, a big part of it was, can we show that these do exist, that it was an observational bias, that we didn't have a large sample of these before, and not that something is horribly wrong with all of our models of stellar evolution. But the point of finding them was not just to say they exist. It's now, what science can we do with them? So there are sort of 3 directions I wanted to go, as I talked about at the beginning. I want to talk about population statistics, mass loss rates, and binary properties. So that's what I want to spend the bulk of my talk on now. So diving in first, what we're working on now, in the paper we have published thus far, there were 25 objects. That was a sample from an initial study that we had where we got spectra of some of the objects. But we would like to know, or at least every time I give a talk on this, someone asks afterwards, is the sample of discovered objects enough to explain blah, where blah could be, is it enough to explain all hydrogen poor core collapse supernova? Is it enough to explain some other type of population? Is it consistent with the expectations for how many we thought there should be? This is very common, and it's a very valid question. My reaction has mostly been, this is really hard to actually say, but I want to now unpack that a little more for you. How are we moving towards trying to actually be able to answer this question for you? So we need 4 different things to do this properly, to actually understand whether the number of objects we see makes sense or if we still need further modifications to our models for binary evolution. So this is sort of four things, sort of two bigger tiers. So first, we need to understand how many objects did we actually find? And there are two pieces of that. Actually having a very well-defined set of photometric selection, and then we actually need to confirm those sources and assess what other possible contamination we might be finding in our photometric sample. And then we do need to understand how many objects should we have found in the first place. And the two halves of that are the binary population synthesis, which itself has many uncertainties in it, and then also a detailed characterization of what sort of selection effects we are actually dealing with in our survey. So I'm going to spend a couple slides on each of these, showing you some work we've been doing towards basically working on all four of these things. So I'm not going to give you a final answer on whether the number is right, but I'm going to show you what we're working on to be able to answer this properly. So first, well-defined photometric selection of candidates. This is something that Bethany Ludwig, who, as I mentioned, just moved to Leuven from University of Toronto a few months ago, has been working hard on for a long time. And you should see publication on this probably on the archive within the next month or so. So with these UV catalogs that Bethany produced during her PhD, and will soon be published as well, there's now UV magnitudes for several 100,000 sources towards both the large and small Magellanic Clouds. And what Bethany has done is she has gone through this quite carefully to actually select a large photometric sample of candidates for stripped helium binaries from the sample. There's about 900 objects total between the LMC and SMC that she has identified. And these are sources that not only fall in this region of the color magnitude diagram that I described before, where you're sort of bluewards of the ZAMs in between the zero-age main sequence and what you'd expect for isolated helium stars, but also have gone through a number of other tests, such as vetting of their SED shapes for quality control, vetting to make sure they are actually seem to be consistent with membership of the Magellanic Clouds, and a number of other things. Again, about 900 or so of these candidates. And you can see just an example here of what their spectral energy distributions look like. And broadly, they are consistent, same with the set of sources that were published in the paper a few years ago, with being consistent with helium star plus main sequence binaries, where you see different contributions, flux contributions from a main sequence star or a helium star. Some of them, like the ones shown here on the left, show very blue SEDs that seem almost consistent with, again, being dominated by a very hot helium star. Some seem to be consistent with needing about equal contributions from two systems, and some do show this excess UV light, apparently in our analysis, but probably are more dominated by a B-type star. So again, this is just giving you a sense of what types of things are in this catalog of hundreds of objects of candidates. But of course, at that point, those are photometric candidates. I mean, those SEDs look nice, and they have properties that are consistent with these, but we do want to do a better assessment of actually confirming and assessing what else could be in this region. And there are a few things I want to mention on this, just to sort of hone in on people what else we might be seeing. So one of them is that when we look at this, what we assume for extinction along the line of sight to these objects is probably the largest uncertainty we find when trying to select photometric candidates for stripped helium stars. In the work we have done thus far, so both in the initial science paper and in Bethany's catalog identifying these sources, we are assuming just a single uniform extinction, which is one example I'm showing you here. For the LMC, we're assuming an AV of 0.38 magnitudes. We're assuming a single uniform extinction along the line of sight towards all objects. We are not doing object by object modeling at this stage. We could go into grave detail about why that is what we're doing at this point, but eventually we want to move towards object by object modeling, but ideally we would have spectroscopy to also do that. But the one consequence of this is that two sides of it. One is that you could have some low main sequence stars in regions of particularly low reddening that could, if we are overcorrecting for the extinction, appear in our analysis like they have excess UV light, even if they truly do not. Now, our extinction corrections on all were on the low side, so these would have to be systems with exceedingly low extinction along the line of sight, but it is still possible some of them could scatter to this region just to the left of the zero-age main sequence. And the flip side of this is that if some true strip stars are actually in regions of higher extinction than what we assume, then we would not find them via our current selection method. They would still appear to be redwards of the ZAMs, but that is because of the reddening as opposed to the true intrinsic spectral energy distribution of the source. So that is one of the largest uncertainties in this. The other thing to keep in mind in terms of assessing contamination is that some other classes of objects can actually exhibit similar temperatures and luminosities to these intermediate mass stripped helium stars. So some examples that I'm showing here in the dashed lines, these are actually tracks for the sort of post-AGB phase for 1 to sort of 6 solar mass stars, which you can see in sort of the final stage when they're curving around heading towards being white dwarfs. They very quickly, this is a short-lived evolutionary phase, but they can stream through this region of the HR diagram. In addition, there are a few models that say that if you have white dwarfs accreting at very high rates, sort of rapidly accreting white dwarfs is what they've often been called, you could also push up into this luminosity range as well. So there are a couple of other types of sources that intrinsically could appear in this region of the HR diagram as well. So what we've been doing for that is we have had campaigns for a couple of years now using a combination of Magellan, IAU Omega on the Anglo-Australian telescope, and now Gemini and VLT, where we are trying to confirm more of these candidates to actually understand spectroscopically what is in this sample. And I can say many of the objects appear similar to what we've published thus far, but there are a number of types of objects, especially as you move to lower brightnesses or luminosities, where different types of spectral morphologies are starting to appear, indicating we might have other types of sources as well. Okay, so moving on to how many objects we think we should have actually found in this region. This is a binary population synthesis question initially. A number of groups are working on this. One I would like to highlight is Beryl Hovers-Afterbach, working with ILVA, recently put out a paper where they do a set of binary population synthesis for strip stars at a range of metallicities from Milky Way up to very low values. And they put out predictions for how many of these stripped helium binaries do we predict in these regions. And just some highlights for you. If we take the helium stars that will actually explode eventually as supernova to be above about 2.6 solar masses, they would predict that there's about 800 such sources in the LMC and about 200 in the SMC. If you extend that to helium stars with lower masses, this can increase up to a factor of 7 or 8 higher than that. But obviously, this does depend as well on uncertain prescriptions within your binary pop synth. So then the last thing I'll mention on this part that we've been working on is, in order to also really do these rates, is we need a detailed characterization of what selection effects or recovery efficiency we're actually getting for different types of binaries. So that's what the population synthesis predicts. Should we have seen them all with our UV selection method? So on a very high level, and I want to spend some time on this because I'm not sure in conversations I've had, this hasn't always sunk in. How we are doing this, where we are looking for excess UV light, it really works best when the strip star contributes a non-negligible fraction of the flux. So that's obviously true in the UV. You need it to be contributing enough to the UV to show up as this UV excess. But in practice, what we found when we comparing grids of models was that systems really only show up bluewards of the ZAMs if the strip star contributes something like at least 20% of the flux, even in the optical. If it's less than that, it's just going to mostly appear right on top of the ZAMs because the strip star is just so much fainter than its main sequence companion. Another way of looking at this is just an example where we've taken the photometric sample and tried to do SEV fitting for them, is that we are mainly sensitive with this UV method to strip stars with masses where the strip star mass is between about 1 to 7 solar masses. Again, these are stars originating from things maybe 6 solar masses up to 20 was where the initial mass they would have come from, with main sequence companions that are less than 5 solar masses or so. And this is somewhat mass dependent. Anything in gray here is something that would not have shown a UV excess. So again, a range of strip star masses we're seeing, but only really things that have 5 solar mass main sequence stars or below are what we're actually thinking. If it was a strip star with a 10 solar mass main sequence companion, it would not exhibit a UV excess that was detectable via our method. So in practice, what this means, I just want to hone in on, is when you select stars with this UV method, you're primarily sensitive to systems with either compact object companions, so things that the companion is not a luminous star in itself, that would pop out like so very easily in our method, or systems that underwent non-conservative mass transfer. And the reason I say non-conservative mass transfer is that if you take something like, a 4 solar mass strip star would have originated from something like a 15 solar mass initial mass star, there's like 10 solar masses of hydrogen that had to come off. It clearly did not get dumped onto the companion if the companion only is 4 solar masses now. We don't know what fraction of it went on, but you could not have taken the entire amount of mass that was stripped off of this star and put it onto the companion. If you did, we would not see it via a UV excess method. So there are other methods to try to identify such systems, but this is what we can find with the UV excess method. So in the original 2023 paper, we very back of the envelope estimated that something like 10 to 25% of binary systems with hot strip stars should exhibit a UV excess. But just really want to emphasize this is incredibly dependent on various prescriptions in your binary pop synth. In particular, things like how are you treating the common envelope, which is obviously a very clear example of non-conservative mass transfer. And in addition to this is mostly me ranting for a while and why this is a hard question to answer, but there are other parameters that impact our detection efficiencies as well. As I mentioned before, what the true line of sight extinction is towards a given object will dictate whether we actually would have seen it in our photometric selection. And also in the UV images, we are less sensitive in regions that have very high densities and crowding. As I mentioned, Bethany developed this pipeline to do point spread function photometry on the Swift images, but it still has a 2.5 arcsecond point spread function. And so that means, in some regions, I'm just highlighting a few examples here, there could be these quite dense regions where you actually see these are dozens of objects. And in this case, it is very difficult to actually disentangle what light is coming from what object. So while we are very careful in our photometric method to not quote magnitudes for things unless we are confident in what we're driving, what this means is that we are much less complete in the densest regions of the Magellanic Clouds, and you do expect some stars to show up there. So our solution to this and what we're working on now is to actually characterize this selection function for our parameters well, is to do a full forward model from the predicted binary stellar population from PopSynth all the way to a predicted set of UVXX candidates, where we are including this all the way through injecting the sources into the UV images themselves and actually seeing what we recover. This is work that's led by Lisa Bloomberg, who's a PhD student at Caltech, working with Karim El-Badri. She's been working closely with Bethany Ludwig on this process, along with Ilva and myself. So just to highlight for you what this process looks like. Lisa is basically starting from things like star formation history maps of the Large Magellanic Clouds. This is from Harrison Zritsky. Sorry, the text didn't show up there. You can then take the star formation history coupled with the population synthesis and decide for each chunk of the LMC and FMC what type of stellar population should be injected there, including both single stars and binaries. You can then develop a model, and this is what Lisa's been spending a lot of time doing, for basically a model for, as you're projecting stars, both how the stars should be distributed along the line of sight and also the dust, and where you use various constraints from different dust maps for total line of sight extinction as well as foreground Milky Way extinction. But she's basically building a map to be consistent with all of the available data for where stars get distributed along the line of sight and where the dust is, and therefore for this simulated population, what the true line of sight extinction towards each individual star should be. She can then go through that and make basically this fake population where you see this is now the same color magnitude diagram we had before. You have certain objects. These are all synthesized or mock populations. And you see like some of these stars here are stripped helium binaries that are showing up redwards of the Zans, and some are bluewards that we would have found. And you can see when you actually look in detail, this is the same population, but now color-coded by what the line of sight extinction is in her mock population. You can see that, you're recovering what I talked about before, that most of the ones we find via our method here, so ones that are showing up between these dashed lines, are things that had low line of sight extinction. Whereas if there are true strip stars that have high line of sight extinction, which are the darker blue in this here, we would have not found them. But she is now able to characterize for, again, this mock simulation, what fraction of the systems are expected to have higher extinctions versus lower, and actually help us characterize our selection function there. And what she's working on now, closely with Bethany, is to actually take this and now inject her fake population into the Swift UV images and pump them through the same pipeline Bethany developed for the photometry and the candidate selection to see which fraction we actually recover for crowding. And what this basically allows us to do is then you go from population synthesis to predicted population, and then you can test different binary predictions and see what matches our observed population the best. So in conclusion, I get asked this question a lot. This is actually really hard, but we are working on it. And I would say, order of magnitude, the numbers look good. And then obviously, the devil is in the details, but we are working on it. Okay, in the last 10 minutes here, there are two other things I want to talk about. One is characterization of mass loss rates for these stars. So what we have is the population of stars that we found in the large and small Magellanic Clouds. The biggest thing I want to emphasize here is that these stars, I'm showing you in sort of the darker color here, primarily showed absorption line spectra. This is distinct from what you'd expect for sort of higher mass Wolf-Rayet stars, where they show these very prominent emission lines, which are due to strong stellar winds. And this emphasizes the question of what do the actual winds look like for these strip stars that are at these intermediate luminosities between Wolf-Rayet stars on high luminosities and subdwarfs at low luminosities? There have been a range of theoretical predictions for this. I'm going to go kind of quickly through this because I'm already telling I'm moving kind of slow. One of them is just if you extrapolate mass loss rates from sort of the higher mass Wolf-Rayet stars downwards. One is if you take theoretical mass loss rates for subdwarfs and extend through them. But, again, these are mostly, this is just an extrapolation. There have been some recent theory work suggesting that these are probably overestimated. This, for example, was one set of models put out by Ulrich Fink in 2017, which put a sort of lower estimate on what the mass loss rates at these intermediate luminosities should be. There have also been other prescriptions coming at it from the high mass end that sort of say as your stars actually go from the Wolf-Rayet regime and get to lower and lower Eddington factors, you might actually basically fall off a cliff in terms of what the predictions for the mass loss rates actually are. So you can see there's a huge span of possible predictions in this intermediate luminosity range for what the mass loss rate should actually be. And I want to emphasize this is really important. It might seem like a detail, but it's really important for a number of reasons. What the wind parameters of these stars truly are is going to affect the final surface composition. So things like what type of supernova will they explode at. They're also going to affect what the radii are and what their future radius evolution is. So it will impact if these stars, for example, will undergo another later stage of binary interaction. And so should affect things like how many neutron star mergers are you actually predicting from binary pop synth. And in addition, the wind parameters really affect the amount of ionizing radiation that can actually escape the stellar surface and contribute to stellar populations that we see, for instance, in high redshift galaxies with JWST. So it's great to actually be able to probe this. And this was something that Ilva did already in her paper using just the optical spectra that we already have. I'm just going to walk you through one example here, where again, we only have absorption lines in these spectra, but that still allows you to place constraints on what the mass loss rates can be. So this is an example where I'm zooming in on the helium-2 4686 line. I'm just going to quickly step through for you if you go from sort of a high mass loss rate of something like 10 to minus 7 solar mass per year, which is similar to what the extrapolation from the Wolf-Rayet winds would have predicted for this luminosity of star. You can see we would have predicted you have emission lines at this helium-2 4686. We clearly do not see this. This is indicating the mass loss rates have to be lower than this. Then, if you sort of zoom in more, if you go down to 10 to the minus 8 solar mass per year, you can see that, this is clearly doing better. Already at that point, you're predicting an absorption line instead, but it's weaker than the type of absorption line that we already see. If you extend this now to 10 to the minus 9 solar mass per year, you do better in terms of the depth and not seeing infilling in this line that would be due to a wind. So in this case, we were basically saying that the optical spectra essentially constrain the mass loss rates to be less than about 10 to the minus 9 solar mass per year. Below this, we can't say because it sort of mostly predicts a similar line. And when you look at the full sample, you see something like this. We do actually are able to place constraints on the mass loss rates for 2 of the sources, but for the rest, it really ends up as these upper limits at around 10 to the minus 9 solar masses per year, which are actually quite low, even compared to a number of the theoretical predictions that are out there in the literature. And again, this has implications for many things, from supernova to neutron star mergers to ionizing radiation. So what we're trying to do now is, how can we do better? And HST is something that has the possibility to help because UV spectra have a number of lines and transitions that are much more sensitive to the winds than what we have in the optical. So this is just an example showing a set of predictions for models that would fit one of our stars in the optical, but have very different morphologies predicted in the UV. So up to this point, we've actually obtained UV spectra for about 10 of the sample, and we're working to model them now. This is work led by Debashis Bhutta at ISTA, working with ILVA. And just as a teaser of one of them, he's working hard on this now, but this is one example of one of our spectra. This is star 6, the same one that I was showing you in the diagnostics above. And ignoring the things in gray are geochronal lines from Earth. But the main thing I want to emphasize is that in a lot of these stars, even in the ultraviolet, we are seeing primarily absorption line spectra, which again indicates we're not seeing strong P Cygni lines due to winds, which really point to low mass loss rates for a number of these stars. Okay, last thing I want to touch on is binary properties and companion types for a lot of the systems that we're seeing. So if, as a reminder, at the beginning, when I first talked about discovery of a population of these stripped helium stars, I highlighted that we sort of had 3 spectroscopic classes in that initial paper. Ones that seemed to be dominated by a strip star, ones where we thought we saw lines from both hot strip star and a main sequence companion, and ones that are main sequence dominated. Here I'm going to be focusing on the first 2, because those are ones where in the spectra themselves, we are seeing evidence for the hot strip star, not just in the spectral energy distribution itself. So we want to understand, okay, what are these actual systems? First of all, are they in binaries? And what might the companions be? And what can we learn about the binary evolution from them? So first, just highlighting again what constraints we get just from the spectrophotometric fitting itself. So in her 2023 paper, when Ilva did spectral modeling, she was presenting spectral modeling for this first class of objects. So the ones where the spectra really seems to be dominated by a strip star itself. And in this, she was able to show that you are able to get a good fit to the spectra of these objects, assuming that only a strip star contributes, that we do not actually have basically any flux contribution from a main sequence star. Now, she did a number of tests to put constraints on that, and how even if you include something like a 10, 20% or a 10-ish% flux contribution, it doesn't change the properties you derive significantly. But we can also ask the question of, could a luminous companion be hidden and just not visible in our spectra, and what constraints can we place on that? And that's mostly, this is kind of a complicated plot, but this is what's showing here, where mass of the strip star versus mass of the main sequence star. And the main thing I want you to hone into is the darkish purple ones here. So both the circles here and then the contours here are where we would predict that it would appear to be dominated by a strip star, like this first class, even if there was a luminous companion there. And so the main constraint is that it is a function of mass, but for sort of the mass range of the strip star, what you could hide is somewhere, if you have a 2 solar mass strip star, you can only hide about a 1.5 solar mass main sequence star and not see it. Whereas once you're up at a 7 solar mass strip star, it could be something like a 3 solar mass star and could be hidden. But those are constraints where either we have, compact object companions, or you have low mass main sequence stars such that they would remain hidden. Alex LaRoche, who is a PhD student at Toronto now, has been working to expand that spectrophotometric fitting to also include that sort of second class of object now, the composites, where we see evidence for both the strip star and the main sequence star. This is preliminary work, but the biggest thing I'll emphasize here is that the circles here are what he's getting for constraints on the helium stars, and the diamonds here are constraints on the main sequence companion. And the biggest thing to emphasize is that these are, again, low luminosity main sequence companions that we are finding here. This is something like, if you convert them to masses based on these luminosities, you'd be getting things in the range of maybe 2 to 4 solar mass main sequence companions. So again, really honing in on like idea of like, these are systems where they really have low mass main sequence companions, or in some cases, maybe compact objects, but really pushing you towards systems where you're probably undergoing non-conservative mass transfer. But in either case, we would really love to have constraints from radial velocity monitoring to understand what these binary systems actually are. So we conducted a large program for this over the last 4 or 5 years ago, basically gathering multiple epochs per star to actually constrain the binarity for these. And I'm just going to show you some results from this as well. Basically, this is one example, again, of star 6. This is sort of our canonical example showing you radial velocities we have over time. You can see it varies a lot. If we just look right now, even before getting into orbits, on what are constraints on the delta RV max, or sort of the maximum RV shift we see for our various systems over time are, I'll start this before jumping into orbits. And the main thing to emphasize here is that you get higher values of this delta RV max parameter if you have short periods, higher masses, or higher inclinations. So let me just show you what results we have now. This is also preliminary work. These are constraints on what we're getting for those helium-type stars, the ones that are dominated by the helium star. Sort of delta RV maxes from about 20-some to up to 150 or so. And this is what we're getting for those composite systems as well. So already this is intriguing to us because it seems like these systems are probably not just a continuum, but there's something truly different about these two classes. That probably the composites have something else going on, either different types of periods, different companion types, or some sort of inclination bias in the sample. But for the ones where we do have strong detections and properties like this, we can go through and actually compute orbits. The ones I'm showing you here, Alex LaRoche is again working on. And the main thing I want to emphasize, again, for these helium stars is that the orbits we are finding for them range all the way from only a few hours up to about a year or so. So again, a huge range of types of properties we're seeing for these systems. Again, emphasizing they probably have multiple evolutionary histories behind them. Now, in many cases, you can turn this into a constraint on the minimum mass of the companion, and it ends up being around a solar mass or so. And again, those are types of minimum masses that if it was around that value, we could not formally rule out that it is a very low mass main sequence companion to some of these systems that appear dominated by a strip star. However, there's one example I want to highlight where that is not the case. This is a system that Bethany Ludwig is currently writing up a paper describing. It is one of our systems that has the shortest orbital period of about 4.2 hours. The minimum companion mass in this case is 1.2 solar masses approximately. However, given this orbit, you cannot physically fit a main sequence star of that size inside it. So this is one example in our sample where you absolutely have to have a strip star. In this case, it has a mass of about 4 solar masses with a compact object companion. So it is possible what we are seeing is a system that is sort of this phase of the evolution, where you're sort of in that final stage before the second supernova that might lead to something like a neutron star merger. But this is work in progress on the physical interpretation and modeling of this system. Okay, so with that, I will leave you my summary. We, through a process of UV excess, discovered a population of stripped helium stars in the Magellanic Clouds, and we've been working hard on where we're going now is trying to understand their population statistics, mass loss rates, and binary properties. And I think, given the time, I don't have time to really talk about this, but there are a number of other fun things we can do with this data. For example, using the same catalog of UV data, Anna O'Grady, who again was a PhD student at Toronto, now a postdoc at Carnegie Mellon, has been looking and characterizing the population of yellow supergiant binaries in the Magellanic Clouds. And these are systems that have implications for things like supernova progenitors of partially stripped supernova, as well as other things. And I think I do not have time to show slides on that, but I encourage you to talk to Anna and look up some of her papers as well, and mostly highlighting that this sort of UV data of the clouds is going to have a lasting impact moving forward. So thank you very much.
Thank you very much, Maria. Very clear talk and very, very interesting results. So now it's time for questions. If anyone wants to ask to Maria. See that today we have many people. So Andreas, yeah, please.
Yeah, thanks very much, Maria. Very nice and very comprehensive talk. I was wondering, since you say you have a few more stars, so in the partially stripped stars that we studied, the typical companion is a BE type star, and I was wondering if you have any BE companions, or do they seem to be completely absent when the star is fully stripped?
Yeah, what I would say there is that in our sample, we do not have any BE stars. However, I would not jump to the conclusion that that means that they are absent when the star is fully stripped, mainly because, what's a good slide to show this on? I do think really this point, I tried to make that what we are sensitive to, basically, my impression is that you might get a B star more commonly when the mass transfer is a little more conservative. So you're basically absorbing much more of the material, enough to the point where the star cannot fully absorb it all. But if you start having a very sort of more massive main sequence companion, which you might expect if you're dumping more of the mass onto the companion, it might be the point where the B star itself is so luminous, it completely dwarfs even the fully stripped hot strip star. And we might not have, with as far in the UV as we go, we don't have the leverage to actually still see it. So some things that could help with this are, if you were able to go farther in the UV, this would help. Obviously, there are like limits to how far we can go, though, but it might just actually be that many of the cases where you see the B stars, the B stars themselves are so luminous and massive enough that, yeah, you don't see the strip star, because it would need to be one that's less than about 5 solar masses or so. Once it gets much bigger than that, it's completely dwarfing these strip stars in terms of the actual, even the UV light from them.
With the NUV photometry that you have then, I guess.
Yes, exactly.
Okay.
Yep.
Okay.
And yeah, you'd get more leverage going further in the UV. Yeah.
Okay, thanks a lot.
Any other question by the audience? Jaime?
Hi, Maria. Wonderful talk. Thanks a lot. So I was wondering about some of the prediction of the binary evolution models. So they predict a very strong helium enrichment in strip stars. But what we have seen in some of these immediate progenitors, like these bloated strip stars, is that there is not really that much helium enrichment sometimes. So I was wondering if maybe some of your systems that look like where the like the main sequence star is the dominant star might actually be just still strip stars, but they do look more like a normal B star.
Oh, interesting. I think I see so you're wondering whether, yeah, so going to like this class at the bottom where we do not actually see a hot star there, but the SED looks like it is bluids of the ZAMs, whether like that star itself could be a partially stripped. I mean, that's a good question. You do expect actually some cases, I mean, it is a small sliver of cases, but you do expect some cases where even if you have a hot strip star, you can have cases where it contributes enough to the near UV photometry to pull it a little bit blue, but your main sequence dominated. But it is a good question. We have not actually gone through with this subset of the population and done spectral fitting for that subset yet to see, is there anything we can tell about the actual hydrogen or helium enrichment in those systems themselves. So yeah, we haven't done fitting on that sort of class 3 objects yet. So,
right. Thank you.
Jaime. Yep, Sally.
Oh, fantastic talk, Maria. I learned so much. I was wondering if you could say a little bit more about the orbital eccentricities. I saw that you had something up on one of your slides.
Yes, and then I didn't mention it because I was talking too much. Yeah, let me pull it back up. Thank you. Yeah, so of the ones that we have done orbits for so far, and again, this is about 6 objects, which are all of that, like, of the helium star type, so dominated by that. We do not see evidence for eccentricity in any of them. They are all consistent with circular orbits. And then what I'm showing here is these are essentially, I mean, rough constraints on what those eccentricities could be. But within the precision of our data, here's sort of an example of some of these orbits again. You can see Alex was modeling these, and Bethany with some of the other systems with the Yoker, which is a particular type of modeling for orbits. And you can sort of see from some of these, some of the posteriors like do have slight inclinations in them, but in all cases we find they are also consistent with zero inclination, or sorry, not inclination, eccentricity. Yeah.
You.
Any other question? Not, I'm going to ask something. Oh, yeah, go ahead, Andre.
Yeah, thank you. Thank you for the talk, Maria. This was great. It was amazing. I have a question about the possibility that binary strip stars might be instead accreting instead of losing mass. So I maybe it's a novice question, but I can imagine that maybe there is some evolutionary route on which they end up reaccreting from their companion. Would that be significant for the population synthesis?
That is a good question. Yeah, and I guess none of the ones I was trying to think of a plot here. So basically a situation where, yeah. I think cases like that are most likely, I'm just thinking off the top of my head, cases where you are more likely, well, I mean, it could overtake, because basically it'd be a situation like if we take the top of this route, you have the primary star, it overfills, it socially dumps onto the companion. It really, then you're talking about a strip star plus a companion here, and basically at what point in this picture, the sort of accretor here is not significantly evolving until this one explodes. But if it, especially after accreting, is massive enough, it could even overtake the initial star and maybe dump some stuff back onto it as well. I don't have numbers off the top of my head for how common this is, but you can imagine too, there are situations where you might, and you know, one thing we've been thinking about for some of the strip stars where we don't see a luminous companion, but the minimum mass is down near solar mass, like there are situations where you could end up with a helium star with even potentially a white dwarf companion as well. And that would involve some situation where, you know, there it's again, you dump mass, but then the secondary, like you need to then strip anyway, yes, there are ways to do that afterwards. But you usually involve some kind of like mass reversal in the process. Yeah.
Right. Okay. Thank you very much.
Yeah.
More questions? If not, Maria, I was wondering, I don't know if you've gone in that direction. So what is the number of stars that you have detected in your surveys? So what is the size of the sample you are working with?
Yeah, absolutely. So if we go to the photometric sample, which you'll see soon. So Bethany is about to publish a paper where there are about 900 photometric candidates. We have gotten spectra of a couple of hundred of those so far. Some of it's challenging because some of them are quite faint. You know, even, you know, that's going down to like 20th magnitude in V-band for those. And 900 or so. So we have spectra of a couple of hundred so far and are working to get more of them at this point. Yeah.
Since this is already quite a good number, have you already started to investigate the distribution of these stars in if they are more concentrated in clusters, or probably it's difficult, but
Oh, in terms of their physical location. Yeah. We've done a broad assessment of just, you know, where the photometric candidates are. The thing that I would really caution, though, is that we really are, I don't know if I'd say biased, because we're trying to like quantify that, but in terms of where we can actually see them, the SWIFT data itself really, 2.5 arcsecond full width half max is enough that you really, like, we can't recover the photometry of most of the dense clusters. And
Okay,
so
yeah,
it
it's going
really
to be
is one
difficult.
that, like, there is this bias, like, we don't have really any in the 30 door region, but that's not because we think there's no strip stars in the 30 door region probably, but just if you were to show the SWIFT image of there, like, it's just wild. Like, you're not going to recover the UV photometry from SWIFT for that region. And so that's a little bit why now, yeah, we're trying to quantify that more with like actually injecting sources into different regions, because the pop synth would predict in a region like some of the young clusters, you should have some of those. But we need to understand if you injected them in that region, would we have actually recovered them or not? And that's something we're still working on.
Okay, because I was wondering if at some point, whenever we do these studies of population, we always have like an uncontrolled sample and then a cluster sample to see if there are any, but it's going to be difficult in this case due to
It's
the
going to be
observation
difficult.
limitation.
Yeah, exactly. And I mean, the hope that, this full forward model where, we're simulating a situation and then, using predictions from combination of the population synthesis plus the star formation history maps, where we would actually inject sources into the right types of locations based on what's known about the ages of those regions now. And we can just say what fraction would we recover. But I think at least with this current sample, like, that's going to need to be more the direction we go. There are other UV data sets that are coming that have better resolution that might be able to do that more intrinsically. But with the SWIFT data, that is a limitation right now.
Okay, because jumping to the case of the Milky Way is difficult due to extinction, no?
Exactly, yeah.
Mhm.
Yeah,
Okay.
at least with this method, yeah.
Thank you. So any final question? I want to take the opportunity to ask Maria directly. If not, then thank you very much again, Maria, for this fantastic talk. And yeah, hope to see you soon in the next seminars or somewhere around the world. Thank you very much, everybody.
Thanks, everyone.